Hello, everybody. I'm happy to have so many people to listen to this seminar. We are coming, as already mentioned, from the University of Technology in Graz. We are focusing, this is a university which is quite focusing also on railway engineering, and which increased this in the last years. So my institute is the Institute for Railway Technology and Transport Economics. It's a part of the Civil Engineering department. We have a second institute in the Civil Engineering department, which is focusing on constructive design of railway components. We are focusing on life cycle management, operation, and these questions. And there is a third institute in our university, which is in the Faculty of Mechanical Engineering, which is dealing with railway, with rolling stock, mainly focusing on bogies and things like this. Furthermore, there is a research cluster on railway engineering in our university, so we have quite intensive connection to the railways. And we have also, as one of two universities in the German-speaking area, a separated master, which is called infrastructure. So infrastructure from the civil engineering point of view as an own master studies. What we do in this seminar, in this row of seminars, we had already some on technology, on principles of lifecycle management. Today, we would like to focus on the methodologies of the economic evaluation, because lifecycle management is always a mixture of technology and economic. We need to picture the behavior which we have to analyze within the technology in economic figures, and we need to come to decision making. Therefore, we need data, experience, and understanding of the technology, and evaluation of the systems in the economic, in the sense of economics. The tools are data analysis, simulation, big data, digital twins, and all the methodologies of economic evaluation, which will be the topic today. Please, if you have questions to the presentation, you can interrupt me immediately in putting a question. Or if you prefer, you could keep the question for the Q&A session as you want to do it. Today we are focusing on the methodologies of the economic evaluation, because there are some specific things in railways which need adaptations of the methodologies. The methodologies of the evaluation are, of course, the standard methodologies, but we have to take some things into account. So what we are, how do we understand this? We see the economic evaluation is based on a technical description. We already had discussed this technical description in seminars before. Our way of describing a technical situation is a standard element. That means we look on track side, we look which parameters are there for a certain section of the track. That means how many traffic load, which radii, how is the subsoil, which superstructure, and then all the parameters which influence the behavior of track. And for these parameters, for such a mix of parameters, we could analyze the service life and the maintenance demand of a track. This is possible due to our data situation. I have time sequences of all infrastructure data for track and turnouts and operation and maintenance and components and ages and things like this. And these data we have at the Institute from the Austrian Railways. And we have got these data now in a time sequence of 20 years. So we see how it changes, we see the behavior, and we can do our analysis. And that's the basic. So we have a description of the behavior, we have a description of the technical situation, and now we need to do an economic analysis. So we have to bring our standard elements, we have to change the technical description into cost figures. The input data for all economic evaluations always is a time sequence of costs. And that's what we have to do. We have to change our standard elements into time sequences of costs. There are some main principles which you might say that's, of course, must be like this. Within an economic evaluation of an investment or any decision, we need to take into account all effects caused by that investment. What does it mean, all effects caused by the investment? When you do a decision to use this or that component, track component, and to implement it in your network, there's the first question: how long is the time span which you have to look at? And if you take this sentence as serious, you need to take all effects into account to make a proper decision. We are at life cycle costing, because whenever you put in a component into track, it will influence your costs and track behavior as long as it is in your track. There is no component, or there's only one component which does not cause costs later on, and that's the component which you do not implement. Every component is in the track, has an influence on track behavior, therefore on maintenance demand, and therefore on costs for the entire time it is in your system. That means life cycle view is not just one approach to do decision making, it is a precondition. Otherwise, you would never have a full view of the effects, and you would not know which effects you do not take into account. Are they relevant or are they not? So you have to have life cycle view. That means when we have to take all life cycle into account, so from track, we are basing everything on a cyclic maintenance. So you do an investment, then you do years and decades of maintenance, and when you put the next investment. So we have to take the time span from the investment to the reinvestment. And if we want to have this as a time span for our economic evaluation, we have to have the costs over the sequences of costs over the entire service life. Sometimes we can work with standard elements, sometimes we work with specific data, but anyhow, we have to change from our standard elements to cost sequences. The standard elements are looking like that. On the top, you have a lot of information. We call that parameter. So it is the description below is valid for a section with heavy traffic, so more than 70,000 tons per day in track. We have a good subsoil condition. We have concrete sleepers. We have a 60 kilo rail with standard steel grade. It's in a more or less straight section, so radius bigger than 3,000. It's on a double track line, and there are more and more information about that. That is the description of the track. This is the parameters which are relevant for a certain given track section. And then the standard element tells us under these boundary conditions, such a track will become 25 years so it's 26 year service life because we start with 0. That has a reason in the economic evaluation. And then such a scheme just gives us the information what needs to be done when. So at the beginning, and we have an investment, the track laying, so the general renewal. In some countries, we have a half a year after track renewal, we have one stabilizing damping that is then in the same year, and we do a grinding of new rails, for example, in Austria. And then we damp these lines every 3 years, and we have some grinding actions. Not much more, and you see at the bottom, we have a line which is called small maintenance. Small maintenance, there are all these costs in which you cannot point to a fixed date, but which will occur, and you spread it over the entire service life, but with a trend as this small maintenance increases over the time. This is the information given by the technical description. So we have got 300 standard elements for the Austrian network. 100 of them are economically advisable. So we understand our network as a follow-up of, let's say, 100 different standard elements, because you are in a straight section, then you come into a curve. The curve is another behavior, other maintenance demand, and so on. So we describe our network in a summary of all standard elements. This can be done in 2 ways. It can be done on the one hand, you can do it on experience from the history. That was the starting point. Nowadays, we have got so good data, recording card data, and all information which you can get from measurements and so on. So that today it's data driven, but this is the result. This tells you what you have to be aware of, which maintenance demand will come when you do this investment. And of course, this is valid for one type of rail and one type of sleeper. And if you say, no, I will take another sleeper type, this this behavior would slightly change. When you have another, if you take wooden sleepers, perhaps the service life would be different. Perhaps you have some more small maintenance in the fastening systems. So you get a lot of different standard elements, and we have now to make the decision which of these standard elements is the best one, seen over the entire service life. So this can be formulated in a strategy telling, if I have this situation, I take this component. And today we want to discuss how to come from that description to a technical, to an economic evaluation, telling us it's the option 3 which we would like to use in this case. First step, we have to go from the technical description towards an economic one, and that's very simple. Here it's just mentioned in the year 3 we have to do one damping, but we know how much are the costs for damping, so we just change the amount of maintenance into the costs of maintenance, and then we sum it up per year. And the result is that the costs per year. We do not have revenues herein, we have just costs, because we cannot allocate the revenues to a special maintenance action. We cannot say we have more customers because we have damped the track. So that's not possible. And therefore we have to deal everything on costs only. So we are of course looking for the least costs over the entire service life. But the basic input is already given. And the basic input for every economic calculation is a time sequences of costs from the beginning of service life to the end of service life, because in the next year, it would start again with a reinvestment. This is a time sequence of costs which you can do the economic evaluation. However, we have to take into account it's just costs. So we have to keep this in mind. We cannot make the decision based on the best profit, because if we have just costs, we don't have profit. So we have to go to the least costs. When we have this, when you have this picture, when you see these costs and you see the work which is behind these costs, you can analyze which amount of the total costs of service life within the service life are caused by investment, which portion is caused by maintenance. And there is a third point, which costs are caused by the maintenance operation or investment operation, but are not infrastructure costs. We call these costs of operational hindrances, meaning we are doing a track work anywhere outside in the network. We are, let's say, a simple example, we are tamping. When we are tamping a section, we are hindering the operation. No train can pass can go on that track where the tamper is working. At least hopefully no train comes in that section. So that means for the operator, he has additional costs. He has costs because he has delays, or perhaps if it's a whole line is closed, he has to run another way. He has to use another route, or he has to do a bus service instead of the rail service during the time of that work. These are costs which are not paid by the infrastructure. They are caused by the infrastructure, because if they would not do this job, the operation could go on, but it is not paid by the infrastructure. So we could say it's not important for the infrastructure company. And that's true. It's not important for the infrastructure company, but it is very important for the railway system. And there is one sentence which we already discussed. When we do an economic evaluation, we have to take all costs into account which are related to our project. And all costs are also costs which are not within the infrastructure, but within the operator. And it is not important if these costs are paid by the infrastructure or not, but these costs will occur. And we will have to take it into account. Otherwise, we would not find the systems optimum. We would just find the infrastructure optimum. Let's have a look on this separation, on this cost composition. We are always basing our calculations on average annual costs over the entire service life. And the total costs, of course, are 100%. And this is an example for a high loaded line. So let's say 150 trains per track and day. And then we learn that the biggest cost portion, by far the biggest cost portion, is the depreciation. And then we have two cost portions which are more or less the same, and that's maintenance costs and its costs of operational hindrances. So the costs which are caused by track work are in about the same like the maintenance. This is a huge amount of money. We have if you look such a cost composition, there is only one conclusion possible to optimize the system. And that is, or let's take it another way. If we want to optimize that system, we want to reduce the red bar. We want to reduce the total life cycle cost. We could do that in three ways. We could try to reduce the green bar, the blue bar, or the yellow bar. If we reduce the green bar, we reduce the most important cost portion. But the green bar is depreciation. Depreciation is investment per year. So we have a chance to reduce the green bar if we can create a track, a superstructure, which has got a remarkable long service life. And in this case, it even can cost a little bit more than the existing tracks. An innovation may have higher costs if it has a good extension of service life. Then we could reduce the green bar, and that in any case would reduce the total life cycle costs. On the other hand, the maintenance costs, if we try to optimize the system in reducing maintenance costs are roughly 20% of the total. So if we reduce maintenance costs by 10%, we would have only a decrease of the total costs by 2%. That's nothing relevant and can happen, it's not stable. So if we want to reduce total costs by reducing maintenance costs, you have to reduce the maintenance costs by far. Let's say, for an example, let's go for a reduction of maintenance costs of half. So 50% reduction of the maintenance costs. That would give 10% reduction of the total life cycle costs. But what would be the consequence, in your opinion, if you reduce maintenance to the half? In the first year, there would be no problem. Track would not react immediately. In the second year, perhaps not. In the third year, perhaps not. But then you see, okay, I do constantly too little maintenance, and the track quality goes down, and anyone track cries for maintenance. But whenever track reacts, you cannot solve the problem in doing more maintenance. In most cases, the consequence would be, if you do for years too little maintenance, that you lose service life. So you are reducing the yellow bar, and the consequence would be a shorter service life. That would mean you increase the green bar. And as the green bar is 3 times higher than the yellow bar, this can never be an economic solution. Therefore, this very simple solution shows you that there is only one way to go for a more economic track, and that's let's keep service life high, or better, let's increase service life. This is for track. It looks the total same in principle for turnouts. And so the two most costly components of asset management infrastructure work like this. I have put here the same picture for track once again, and put the picture for turnouts on the second side. Turnouts are a little bit more complicated, so they need a little bit more maintenance. But still, depreciation is the highest portion. So we have in principle the same outcoming. One big difference. Life cycle costs of turnouts are roughly 11 to 13 times higher compared to open track. So this 100% compared to this 100%, then this is 11 times more. The distribution between the main cost portions is slightly different, but it comes to the same outcome, to the same conclusion, and the conclusion is let's increase service life. All innovations, all research on track has the target to increase service life. This will be even more important in future because the target of at least European railways is to shift transport from road to rail. The target, Austria has the best model split in freight in Europe and the second best in passenger transport in Europe. Nevertheless, Austria's target is to double the train numbers until 2040, to double it. And now we run into a problem which gives more importance to sustainability. And this problem is when we double the train number, we will have less time for maintenance. And then this is really a big danger in future. And the only way to solve that problem is to go for more sustainable track systems. We want to increase service life, and the only way to increase service life is to increase quality, because an increased quality is reducing the deterioration, and that gives service life. When we have this distribution, and that's already important for the economic considerations, we will have a look on what are the most important cost factors. If the most important is the initial track quality. If the subsoil quality and the drainage is not working properly, we cannot optimize the track. Then we come into extreme high costs. The factor which I given here is a realistic factor from a given example, which we found in the network, but it is, to say it open, it was the worst case. In worst case, you have 9 times higher, so higher life cycle costs. The next point is switches, density of switches. Turnouts are so expensive that we should build them. We need them, but we should build them only where we really need it. Ballast quality is quite important, and it's underestimated, I think, in a lot of cases, because if you have poor ballast, this can reduce your service life in an important amount, as you see here. Radii, of course, the sharp radii is more expensive. Cost of operational hindrances in extreme case come up to 30% of life cycle costs. Of course, in a branch line, they are not very important. Length of track work section, that's an operation, that's then a question of input data in the economic field. The longer the section which you work, the lower are the meter costs. Traffic density is an important effect, but traffic density is not that bad because railway is a mass transport system and it works. Quality of rolling stock is relevant, and of course all the specifics of high speed or high axle or heavy haul lines. So we have got the time sequences of costs. Having this, we need to choose a proper methodology for the calculation. We always calculate with dynamic economic calculations, static economic calculations do not take into account the costs of money. And as we have so long service lives, these costs are very relevant. So we need to go to dynamic calculations. The dynamic calculation is based on a discounting of the values to a present value. And this means you have the normal time sequence of costs and you discount it with the costs of money. So the costs of fixing money. With this rate, you discount it, and you have taken into account the point of the time of payment, and you can then sum up all the costs, because a payment in the year 9 is not the same value like a payment in the year 0, and this is taken into concern in this discounting rate. So we get a net present value. And of course, if the net present value is positive, you have a profitable project. We have no income. So if you have least net present value on costs, we have the best project. The next possibility, next calculation methodology is the annuity. It's the average annual costs or benefit. This is calculated in a simple way. You have to multiply the annual cost, the net present value, so the total costs of a given service life, with a capitalizing factor, which is just a formula, and you can have the average annual dynamic costs. This is the calculation which we really use, and we have to discuss this. However, you have to define this discounting rate. And this discounting rate should be the net rate of the costs for money in your company, the net rate without inflation. And this is important to do, not to put in high discounting rates higher than your costs on money, because if we have 0%, we are static, every payment is the same value. If we have just the discount rate of 1%, already a payment in the year 30 is only valid with 74%. That's fine. But if we go for high discounting rates, then we contradict the idea of evaluation of sustainability. Let's take the 10% of discounting rate. That would mean that the payment in the year 30 is practically not taken into account. And that would be wrong, because we want to picture total service life. We want to picture the sustainability. There is a proposal by EC for the net discounting rates independence of service life, and they should be for railway maximum 4% without inflation. If the service life is short, you can have more, but in our field, it should not be more than 4%. The net present value, if we set put the net present value to 0, we can calculate the internal rate of return. So we have, we calculate the net present value for a given discounting rate. We can use every discounting rate which we can. Every discounting rate would deliver another net present value. If we take 0, we are on the static solution. If we take more, we come to a function of net present values. This function crosses 0 on any point of that, and that's an important economic figure, because for rates less, so if you pay less than 12.8% for your money, you have a benefit. If you have to pay more for your money, you have to pay more to the banking that you gain than you gain from the project, so it would not be advisable. The big question is always, should we do the calculation with inflation or without inflation? And I want to do this, show this in an example. Either we do it without inflation, And then we have to take the real, so the net discounting rate. If we do it with inflation, we first of all have to calculate in the inflation. So we have to increase the costs in future due to the inflation. And then we discount it with the total rate. The nominal discounting rate is the real multiplied with the inflation. Let's do that in an example of figures to see that clearly. If I have the payment in the year 5, and this payment is 10,000, we assume the real cost of money is 2%, the inflation is 1.5%. So you see that the example is before the inflation now went up dramatically. That would mean that nominal value would be 3.53%. So, and now we do the calculation without and with inflation. The present value is the discounting of this value in the year 5 to the year 0. We have to discount it when we do not take inflation into account. We have to discount it with the real value, real discounting rate. The real value is 2%. So that's the real costs of my money. I have to discount it for 5 years. So I have to multiply the 10,000 with 1.02, the discounting rate, with the power of -5. And that would mean, from today's point of view, this payment in the year 5 has a value not of 10,000, but of 9,000 and something. You can interpret that in that way. If I today put on my banking account 9,075 euros, and I have 2% rate, in 5 years, I would have the 10,000. So for me, today, it's just a value of 9,757. Now we do the same calculation, taking the inflation into account. We have to do it in 2 steps. In the first step, we have to increase the value in the year 5 due to the rate of due to the inflation. The inflation is 1.5%. It is an increasing of 5 years, so it's the power of 5. This gives 10,770 euros. That means my 10,000 of today would be nominal 10,700 in the year 5. And now I will discount this value with the nominal discounting rate. As I put in the inflation, I have to take the total rate. So I take 10,772 and discount it with 1.353% with the power of -5. Now I go to the year 0. And the result is absolutely the same. So you can choose one of the 2 possibilities. Both deliver the same result. I, for my person, prefer the left one because it's simpler. It's more simple. The right one takes inflation into account. But this does not give you any additional information because you calculate the inflation in and out again. So if you would take 100% of inflation and then the nominal discounting rate for this 100%, then you would come also to the same value. So you do not have any additional information. But you have an additional problem. Because if you do the economic evaluation and you do it in railways for the next 30 years, 40 years, who knows the rate of the inflation for the next 40 years. As all the world was now surprised by the increase of inflation, we know that nobody knows it. But it doesn't make any change in our decision making. Inflation does not change the value. Inflation changed the value of the money, but not the value of the system which we are evaluating. Therefore, in the most of European countries, it is calculated without inflation. Then they do not have the endless discussion on rates of inflation, which is not necessary because it's not important what you put in. If we look totally to the economic methodologies available, there are static solutions and dynamic solutions. And the specifics of the railway infrastructure is we have no assignable revenues, so we keep on costs. If we take this, we cannot take the total, the profit. We have to take the annuity of the costs or the internal rate of additional investments and so on. We are taking just the cost side. That means if we go to annuity and we know it is costs only, we are choosing the one with the least annuities. So the least costs over the entire system. We're choosing the cheapest one. But as we are taking all the service life into account, the cheapest one is the most sustainable one. So if we have, for example, this standard element and another standard element which we want to evaluate, it is something is different, and we compare that, it would be very simple. We could use these methodologies. We could use the net present value. But what happens if our solutions do not have the same service level? The net present value is the total costs over the total service level. So, of course, if the option B has a shorter service life, it's very likely that it has shorter costs over the entire service life. Therefore, we cannot compare the option A and B with the net present value. But we could compare it if we do not take the total costs of the service life, but we calculate this down to the average annual costs. Then we can compare it. And that's especially the annuity. So our most important the conclusion for the methodology is we have high service lives. That's very important. Otherwise, we could not afford our system. It's too costly. That means we have high costs and capital commitment. That means we must not do any static calculation. We need to do dynamic calculation, which takes the point of time of payment into account. And as we have got different service lives, normally, when you have an innovation, the target is in general to have longer service life. Perhaps you have more investment costs, but then you have to compare if this option with the innovation is better than the given option. That means you compare different service lives with, and you cannot do it with net present values. You have to go for the annuity. And we do some sensitivity analysis, because when we picture the future, we go into prognosis. When we go into prognosis, we have some uncertainties in the prognosis, and we have to work with this as well. The sensitivity analysis cannot reduce the risk. They cannot make the prognosis better. That's not the target. That's not possible. But they can tell us what happens if the prognosis changes a little bit. And therefore, you can analyze if you have a little bit change in the damping costs. Has this a big influence on your decision? If you change to service life, has it a big influence or not? So you get a feeling where the risk is really coming from. And when we are doing such strategies, what is the result of our economic calculations? So I tried to show you that we are going for the average annual cost, so the annuity, the average annual dynamic cost. What does it cost per year seen over the entire service life? But we know that our input data are, yeah, I know what damping is in the next 2 years. Do I really know how much is the damping in 40 years? I do not know what the development of the damping machines will be. Perhaps they have more capacity in 40 years and the costs are reduced. Perhaps not. I don't know it. So the more in future, the more you have uncertainties in your calculation. That means when we are calculating the annuity for 40 years, so we know the system will keep for 40 years and we calculate what will it cost in average per year 40 times. The only thing which I really know is this figure will not become true in 40 years. There will be some slight changes. So the annuity itself is not the result of our calculation. But what is the result? We have different options. You have a track and you want to calculate if I should take, for this situation, if I should take a standard steel grade, a rail with standard steel grade, or should I take a rail with a higher steel grade? So should I take 260? Should I take R350 HT? Should I take R400 HT? So I have 3 options. And the main result, and I get 3 annuities. And I use these 3 annuities for ranking the options. So with the least cost, that's for me the best option. The highest cost are the worst option. So I have a ranking of these 3 options. And the ranking is the main result, not the annuity. And now I have to check if this ranking is stable, though some of my input data may change. And that's what I'm doing with sensitivity analysis. When I know, okay, my 40 years, it's not clear, is it 40 years, will it be 42 years? I repeat the calculation with 42 years, and then I check, does the ranking change? If the ranking stays stable, I can tell absolutely clear, this option is the cheapest option. It is the best option for, in any case, without knowing totally exactly how much it will cost, but I know that all the other options will be more costly. And with this, I have a basis for my decision making. I can tell the investor, please use this superstructure in that situation. It will be the best you can do. There is one thing which is quite nice, and that's the critical value. So the sensitivity analysis would only be, I'm not sure about the 40 years. Some people guess it is 42 years. Some people guess it 38 years. So I calculated with the other figures, and look if the ranking keeps stable. Another thing is to calculate a critical value. I know I have an innovation which is more costly and which has other effects, and the people expect 20% more service life. But you are not sure about this 20% because you will know it precisely in 30 years. Some people guess it 30 years, some people 20%, some people say it's less. And then you can calculate how much it should be that it can cover the additional costs of the investment. And this is an information, for example, you say, now without innovation, I have 40 years. With innovation, I think it's 48 years. And now you calculate how much increase of service life you need, that this option still is the best option, so that it's equal to the second best. And then, for example, I get 47 years. That would be a bad result. The assumption is 48 and it works if I get minimum 47. That would be risky. If my result for the critical value would be 41 years, then without innovation, it's proven, it's known, it's 40 years. And now I have innovation where we expect an increase of service life of 8 years, but we just need 1 year for showing its economic efficiency, then I have a very little risk on this additional service life. So you can get a feeling about the risk. That's it. That means whenever you do an economic evaluation in field of, especially in field of railway infrastructure, we face the problem that we have to do it for a long period of time. That means you go, in a lot of cases, you have to go into prognosis, and prognosis are always more or less precisely. They have an expected value and they have some differences. Therefore, the economic evaluation, which is the basic calculation, which is to give the annuities and to have a ranking, this is not sufficient. Every economic evaluation must have the basic result and then discuss the risk of the decision. So you do sensitivity analysis to get a feeling of the risk. That's the theory. So if we come to the question of asset management, and we are now in the evaluation, we have 3 questions within asset management. The first question is, which component should I use? That's an investment strategy. And please, you cannot calculate this for the average track, because the average track does not exist. The average track is a single double track line, electrified, not electrified, with small radii, more straight, heavily used or little used. This is the average. You don't have it anywhere. Therefore, we split it into different parameters, into different typical situations. And for every typical situations, you have to do your economic evaluation. The outcome is that you will have a strategy for components which differs. You will use in a straight line another steel grade than in sharp curves, because in sharp curves you have much more wear, so you need a more wear resistant rail. In the straight curve, where the flange never touches the rail, you don't need this wear resistance. So you have specific solutions. That is the first question. The second question is the maintenance strategy. But when you now go through what I said up to now, you cannot answer the investment question without taking the maintenance into account, and you cannot take the maintenance strategy, calculate the maintenance strategy without knowing what is the component which is in use. So investment and maintenance strategy for their own cannot exist. You have to calculate it together, and this together is pictured in the standard element. And the third question, which we have to answer in the life cycle life cycle management, is how long should I keep my track in operation? There is a point in time where, when the track grows old, the maintenance increases and you have to do more and more maintenance, and anyway, this is not economic anymore. And you have to find this point in time, the proper point in time, where you should stop the game and go for the renewal. And this, how to do this, we will discuss after the break.